So we're going to kick off our look at sort algorithms by starting with bubble sort. I want to say right up front that this algorithm's performance degrades quickly as the number of items you need to sort grows, but it's a commonly taught algorithm and you might hear about it, so we'll take a look at it and it'll get us warmed up for the rest of this section. So I'm going to start out by explaining how the algorithm works. So I have an array on the screen. It's an array of length 7. So it can store 7 integers. At index 0, we have 20. At index 1, 35. At index 2, minus 15. You can see the rest of the array there. And we want to use bubble sort to sort this array. Now, the way that bubble sort works, and you're going to see that this is pretty common with sort algorithms, is as the algorithm progresses, it partitions the array into a sorted partition and an unsorted partition. And this is a logical partitioning, so we don't create completely separate array instances, and we have an array instance that contains what we've sorted so far and another array instance that contains unsorted numbers. No, everything is done when it comes to bubble sort using the array that we're sorting, and we partition the array logically, and you're going to see this when we go through the algorithm in just a minute. So when we start the algorithm for this array, we're going to have a field that we're going to call unsorted partition index. And when we start, this will be 6 because the entire array is the unsorted partition when we start out because we haven't sorted anything yet. So 6. It will be the last index of the unsorted partition. All right, so the implementation that I'm going to show you starts at the left of the array, or at index 0, so that's what I is. And what we do is we compare the element at index 0 with the element at index 1. And if the element at index 0 is greater than the element at index 1, we swap the elements. If it's less, we don't do anything because, of course, we want to move larger elements towards the end of the array or towards the right because we're sorting in ascending order. So in this case, 20 is less than 35, so we don't do any swapping. And then what we're going to do is increment I to 1. So now we're going to look at the element at position 1 and compare it with the element at position 2. And in this case, 35 is greater than minus 15, so we swap them. So now minus 15 will be at position 1 and 35 will be at position 2, and we increment I to 2. So now we're going to compare the element at index 2 with the element at index 3. 35 is greater than 7, so we swap them, and we increment I to 3. So now we're going to compare the element at index 3 with the element at index 4. 35 is less than 55, so we don't do anything. We just increment I to 4. And then we compare 55 to 1. That's the element at position 4 with the element at position 5. 55 is greater than 1, so we swap them. And we increment I to 5. And finally, we compare 55 to minus 22. And of course, 55 is greater than minus 22, so we swap them. And at this point, I is equal to the last unsorted partition index, so we stop. We have completed the first traversal of the array, and at the end of that traversal, the last element in the array is in its correct position. And so at this point, the greatest element in the array will be at index array length minus 1, which for our array is, and for our array length minus 1 is 6. So at this point, what we're going to do is we're going to set the unsorted partition index to 5 because we now consider position 6 to be sorted. And so the logical partition is going to be between the element at index 5 and the element at index 6. Everything from index 5 down to the front of the array is in the unsorted partition, and everything at array index 6 and to the right, and in this case there isn't anything to the right, everything there is in the sorted partition. So on the next traversal, we can see that 55 is now in the sorted partition, and we set I back to 0. Because we want to repeat the process we just did. And the unsorted partition index is now 5. So we start all over again. We go, okay, the element at array index 0, is it greater than the element at array index 1? And it is. And so we swap them. And we increment I to 1. And then we say, is the array element at index 1 greater than the array element at index 2? Yes, it is. So we swap them. And we increment I to 2. We say, is the element at index 2 greater than the element at index 3? No, it isn't. So we just increment I to 3. Then we compare the element at index 3 to the element at index 4. 35 is greater than 1, so we swap them. I gets incremented to 4. 35 is greater than minus 22, so we swap them. I gets incremented to 5, and now I equals the unsorted partition index, so we stop. And at this point, 35 and 55 are in their correct positions, and we set the unsorted partition index to 4. So now everything in array index 0 to array index 4 is in the unsorted partition, and everything from array index 5 up to the end of the array is in the sorted partition. And we've set I back to 0 because we're now going to repeat the process. Now I'm not going to go through the other traversals. They'll operate the exact same way. We're going to keep incrementing I, and we're going to keep comparing the element at I with its neighbor and swap the elements if its neighbor is less than the element at I, until the sorted partition is the entire array, and then we're done. Now this is called a bubble sort because depending on which way you're sorting, in our case the larger values in the array will bubble up to the end of the array. And another way of looking at it is to flip the array vertically. So we take the array and we flip it counterclockwise so that array element 0 is at the bottom and array element 6 is at the top. And another way of looking at it is saying that the larger values are bubbling up to the top of the array. Now, as I said, there are some variations where the array is sorted from right to left. So the traversal goes from right to left, and sometimes the smaller elements are bubbled to the front of the array rather than the larger elements being bubbled to the back of the array. But the same steps are used. It's the same algorithm. So that's bubble sort, and so now let's take a look at how this algorithm performs. First of all, it's an in-place algorithm. Now, what do I mean by that? Well, as I said, we're logically partitioning the array. We don't have to create another array in order to perform the sort. And so when it comes to memory, this is an in-place algorithm. Now, we do, as you see when we look at the implementation, we do create some local variables, but that's okay. It's an in-place algorithm if the extra memory that you need doesn't depend on the number of items you're sorting. So we're going to create a few local variables, for example, to store the last sorted partition and to store I, for example, but that doesn't mean it's not an in-place algorithm. If the extra memory you're using doesn't increase as the number of items in the array increases, then it's still an in-place algorithm. It's okay to use a few extra variables. Now this algorithm has O to the n squared time complexity. It's a quadratic algorithm. So that means that it'll take 100 steps to sort 10 items, 10,000 steps to sort 100 items, 1,000,000 steps to sort 1,000 items. So as you can see, this algorithm really degrades quickly. Now, how do we get O to the n squared? Well, we'll talk about this a little more in the next video when we take a look at the implementation. So I'll see you there.